Hello and welcome to the lecture on angular momentum. Here we're going to take a calculus view of angular momentum. All right, so first of all, let's define it. What is angular momentum? Well, it is angular velocity multiplied by the moment of inertia. All right, okay? And most importantly, perhaps, it's the last of the translational quantities that we haven't seen an angular equivalent for, because we've seen rotational kinetic energy and we've seen torque and we've seen the moment of inertia, right? We've seen angular velocity and we've seen angular acceleration. So now we finally have angular momentum, all right? So like torque, for example, angular momentum only has a meaning if it's defined relative to a particular axis of rotation, a particular pivot point. It's meaningless to define an angular momentum unless you have that origin, that axis of rotation location, okay? And that's no different than torque because you have to have a defined moment arm. Same thing here, you have to have a defined moment arm, effectively, or a displacement vector from that axis of rotation. Like translational momentum, it is conserved when no external net torque acts on the system. Now, translational momentum, it would say when no external net force acts on the system, but since we're talking about a rotational idea here, it should be torque. All right, so same sort of idea. There's going to be plenty of times where we have conserved angular momentum. That's going to help us solve certain problems. It is a problem-solving technique, that conservation of angular momentum. And when should we expect there to be no external torques? Well, for events that happen very quickly, like collisions, just like was the case with translational momentum. And in fact, we'll talk about the conservation of angular momentum in the next lecture. Okay? Well, we also have that angular momentum is a vector quantity. It's perpendicular to the plane of rotation with a direction set by the right-hand rule, the cross product. Okay? Now, that's true of torque as well. We already know that torque is perpendicular to the plane of rotation. In fact, we know that omega, alpha, and torque are all perpendicular to the plane of rotation. So we've definitely seen that idea. If you have like a spinning disk, then maybe, and the disk is spinning in this direction, then this would be angular velocity. And you would curl the fingers of your right hand and your thumb would point in the direction of angular velocity. Okay? Now, we've said that for torque as well, but what we're going to do now, what we haven't done in our discussion of torque, is we're going to use the cross product. Now, if I talk about torque or angular momentum, well, we're going to do a little bit of both here. Because this is the section where we kind of formally introduce using the cross product as a method of solving for the direction of a rotational vector, we actually do it for torque as well as for angular momentum. So even though the section is called angular momentum, we're going to be solving a couple problems that involve torque as well. Okay? All right. So we have this idea that torque is, if we're going down to our key equations, we have torque is equal to a cross product of displacement and force, and then we have angular momentum also as a cross product. So this is going to be a key idea, that both torque and angular momentum are cross products of different quantities, mind you, but they are both cross products. So they definitely share that in common. Okay? And we can also go back and forth between torque and angular momentum. They're very closely related. All right? This is going to be the right-hand rule that we're going to be using. There's any number of versions of the right-hand rule. The version where you curl your fingers and then your thumb points in the direction of angular velocity or torque for that matter, well, that's often called like the simple version of the right-hand rule. This is the full cross product version. I like this little figure because it really looks like the fingers are being held like a 3D coordinate axis. And I like that the thumb is the actual cross product. It's the product, all right? And then the A vector has to come first because order matters for cross products. Review the notes on cross products when we were solving them as kind of pure math problems in preparation way back earlier at the beginning of the semester. So review those notes if you need to, or review a math textbook for that matter. But here we have A, pointing at the finger, and then B being the index, with the index finger, and then B being the middle finger, and then the thumb is the cross of those two vectors. And that matters, right? We can't switch these two. That would not be the same cross product. In fact, if we switched A and B, then the thumb would point exactly 180 degrees. Okay? All right, so that's a cross product. This is the version I'm definitely going to recommend using. Okay, so first let's define all the variables here, make sure we're clear on them. So tau is for torque, units of Newton meters, same units of work and energy, but torque is a vector, so it's distinctly different from work and energy, but units of Newton meters. We have R, which is the displacement from the pivot, so the distance from the axis of rotation, R, right? A length vector with units of meters. We have force measured in newtons, a vector of course. Then we have L, okay? Excuse me. L is angular momentum. What are the units of angular momentum? Well, they're joule seconds, okay? How do we know they're joule seconds? Well, if you look here, right, we got momentum, right? Momentum was mass times velocity. So if you look at you can clearly see the units here. So I'll just kind of do a quick unit review. So we have, considering this expression here, and by the way, this expression just comes from the fact that P is translational momentum, P is equal to mv, and then m is mass, which can get factored out of the cross product. You can take a constant out of the cross product. Okay, so the units then would be kilograms, then we have meters, and then we'd have meters per second. Okay, so if you look at that, okay, well then I've got, so that gives me kilogram meters squared per second. Oh, okay, well recall that joules were Newton's times Newton meters, right? Well, Newton meters were kilogram meters squared per second squared. So the only difference here is that it's a second instead of a second squared. Well, that's the same then, if I had a second squared, is multiplying by a second. Ah, so look now, in this box here, that's a joule times a second, hence the units. Angular momentum have units of joule seconds. Now, you can express them as kilogram meters squared per second as well, but I think it's more eloquent and clear to express them as joule seconds. And it's a nice contrast because translational momentum is Newton seconds, right? So when you go from translation to rotation, you go from Newton seconds to joule seconds for your momentum term. And that's true, right? So every time we have one of these terms that has an analogy in rotation, has a translational term, mind it if it's velocity or force or whatever, that has an analogy in rotation, generally, the units change. In fact, they always do. I guess the one time they don't is energy, right? Because rotational kinetic energy and kinetic energy both have units of joules. That's the one time you don't have a unit change. But most terms going from translation to rotation do have a unit change, this being no exception. Okay? Last couple things, mass obviously in kilograms, and then v is in velocity, meters per second. Here's a little 3D axis with x, y, and z. And then we can see if I have a displacement, if the origin is my pivot point, which it should be, right? Otherwise, why would you draw your coordinate system without the origin being your pivot point? Unless I guess you have multiple things pivoting. But so anyway, so here's your displacement vector from the origin shown in green. Let me zoom in a bit on it. And if I have some velocity, well, the velocity is going to point in the same direction as momentum. So maybe I have a momentum vector that's a little bit longer if the mass is bigger, is bigger than 1. But point being that the velocity is going to be parallel to momentum. So if you think about the cross product here, well, it should point in this direction. Okay? I want you to confirm that it points that direction. Use the right-hand rule. I'm going to zoom out so you can see it. Use the right-hand rule. Remember, okay, that for angular momentum, which one's first? R is first. That means that A is R, okay? The A vector is R. The P vector, which might as well be the V vector because they're parallel. So B is P, okay? So then, okay, so hold your finger of your right hand in the direction of the green arrow over here representing R, okay? Then hold your index finger in the direction of the velocity vector, which points straight up. So your index finger should be pointing to your right, your middle finger should be pointing straight up, and so where must your thumb point? Towards you, out of the page. And that is exactly what we see here for our angular momentum, okay? Our L vector, it is the cross, okay? So again, this would be R, this would be P, and this would be L. And then P, of course, just mv, all right? And by the way, if we're doing it for torque, it would be R, F, and tau, okay? Now, in this case, it was really clear because they were all at right angles to each other. And so it's very clear to use the right-hand rule. If you're using the right-hand rule for vectors that aren't at right angles, you need to just consider the components that are perpendicular. And that's what I'm highlighting in this next equation here. That if we're thinking about the magnitude of the angular momentum and also a way to help think about the cross product, we have to remember that it is, first of all, RMV sine phi, where phi is the angle between R and P. Okay? P obviously has a magnitude of mv. This also means that it is equivalent to multiplying the displacement by the perpendicular component of P. This is the component of P that's perpendicular to R. Or we can consider the perpendicular component of R. That is to say the component of R that's perpendicular to P. Right? And that's all I've done here is just clearly show that we always just consider the component of the vector that's perpendicular to the other vector. Because that's the thing about cross products. Cross products are maximum when the angle between the two vectors is 90 degrees. And they're 0 whenever the vectors are either parallel or anti-parallel, which would be like this, okay? In those cases, then you have 0 because then you have sine of either 0 degrees or 180 degrees, okay? All right, so that's the nature of cross products. All right, a couple more ideas. What's going on with this equation right here? We've got a derivative, we've got net torque. What is it? It's Newton's second law. This is the 4th time we have seen Newton's second law, the 4th and final time we've seen Newton's second law. All right, we saw F equals ma, okay? Then we saw that F equals the first time derivative of translational momentum. Wonderful, okay? Then we saw that tau net, and it was F net, by the way, equals I alpha, okay? Also, great, so those are three times, okay? And now we're finally seeing that tau net equals the first time derivative of angular momentum, right? That's very comparable to F net equals dp over dt, isn't it? Right? Same idea. Yes, it is, okay? Except we've just replaced force of torque and we've replaced translational momentum P with angular momentum L, all right? And is this also consistent with tau equals I alpha? Yeah. If we consider that L for solid objects is I omega, then we could factor out the I as long as it's not time dependent, in which case we have d omega dt, which then becomes I alpha, right? So this at least shows, although it does have certain restraints considering that our angular momentum has to be I omega, and then I has to be independent of time. But regardless, it at least shows that in general that this is an equivalent expression of Newton's second law in rotational form, all right? And that idea that angular momentum for solid objects is I omega is really this right here, right? Because if you think about it, taking the cross product of R and P, it's giving you that expression. Because look what this is, right? Mass times R, right? What is mass times R, right? Well, mass times R is actually going to give you almost the units that you need for the moment of inertia. Because you think about it, then what's V? Well, V is meters per second. Well, now you've got mass, meters, and meters, right? Because you got the meters per second in the velocity, you got the meters in the displacement, and you got the kilograms here. Well, look, the kilogram, meter gives us our kilogram, meter squared, which is the proportionality of I. It's the units of I, the moment of inertia. So you can see where we'd have that, especially once we factor out the m, and we're just left with the 1 over second. Well, 1 over second is the same as radians per second. It's the appropriate units of angular velocity. Okay? Now, so this really is always true. So you can say, yeah, it does. It actually even works for a system of particles, but we're really going to use it for a solid object where we have a well-defined I. Maybe it's a cylinder with 1/2 mr squared, whatever it may be. But that would be our moment of inertia, and that would be our angular velocity. Okay? But they are consistent expressions, whether we're thinking about it in the cross product way or the more scalar way of thinking about angular momentum. Now, they do show up in slightly different problems. So really, we're going to mostly be using this cross product definition of angular momentum when we're dealing with a particle. Okay, it's like some particles moving through space, and it's usually translating, but it's translating relative to some pivot point, so we can just define it as having angular momentum. Okay, all right. So also, there's a very nice table here summarizing all the kind of ideas that led up to having this idea of angular momentum and it being the cross product and how it compares between translation and rotation. Go ahead and consider this a very helpful reference table. All right? Okay. So with all that said, let's finally get on to our practice problems. Okay. So we got 3 types of practice problems. Problems that involve calculating torque or angular momentum using the cross product, sometimes both, using the cross product of constant vectors. Okay, so constant vectors. Okay, that's in contrast to type 2, which problems that involve calculating torque or angular momentum using the cross product of time-dependent vectors. All right, so that's going to be the difference. The time-dependent ones are going to involve an extra step. All right, often taking derivatives with respect to time to maybe move from velocity to position, or from position to acceleration, whatever it may be. Okay, functions of time. So these will be functions of t. Okay, and finally, type 3, I just have one example. Problems that involve using Newton's second law to relate torque to instantaneous change in angular momentum. Right, kind of a proof of concept. All right, so let's get to the examples. Example 1. Suppose that a force is given by the following vector. All right, a constant vector, right, units of newtons. Okay, it's got some components in the I hat, j hat, and k components. Remember, I hat is x, j hat is y, and k hat is z. Okay, so these are just the x, y, and z components. All right, it's applied at a particular position given here, right, another vector relative to the origin. Okay, so since we have a force and we've got a moment arm, right, or at least a component of this will be the moment arm, then we have a torque, right? This will create a twist essentially. If maybe we can imagine this as a massless rigid rod or something. Okay, so then the question is, what is the torque vector that is created relative to the origin? Okay, all right. So I like to draw pictures for these. That's not always necessary. Okay, but I think it's very helpful. It really helps you understand it better, and you may be asked to sometimes. Okay. All right, so I drew the r vector. The r vector is in the xz plane. So So we can clearly see, yeah, so it is, and it's got a negative value of x, so there it is, right? And I try to show what plane it is with the dotted lines. So this r vector, if you kind of see it in perspective, is in the xz plane. In contrast, the force vector has components that are, has a negative x component, has a negative y component, has a positive z component. So what I'm trying to show with this one is it's coming out of the page a little bit by the fact that the dotted line doesn't start at the origin, but then it also goes down below the basically below y equals 0, and then it goes forward on x because it has a positive x component. So you should imagine this vector going significantly down out of the page a little bit, and actually in the negative x direction because it's going backwards relative to where it started. See? Okay. All right. So hopefully that the 3D picture is it works. That's the idea. It doesn't have to be perfect. Just has to get the point across. Now let's actually just do the math. So we're going to do the cross product. All right. So again, refer back to when we introduced practicing with the cross product before. The best way to do it is kind of set this up as a reminder of how to group your numbers together and associate them with the correct components of I, j, and k. I hat, j hat, and k hat, that is. All right. So we do this, and remember that if so basically you multiply these two together and then subtract the product of those two. Okay, and then that's what gets attached to I hat. And then you do the same thing for j, but you multiply these two together, and then you subtract the product of these two. Okay, and then for x, you multiply these two together and subtract this product. Okay, and then the one that gets split, the j, is the strange one because it's the only one that has a leading negative. The other ones have pluses in front. Okay, all right. So when we go through, we pick up a couple zeros, right? Because it's we multiply by 0 here, and then we pick up another 0 on the k hat. All right, and then I'm just gonna bring everything together and make sure to multiply all your negatives. And what we get is this. Okay, this is our torque vector, right? Units of Newton meters, right? It's got a large negative I hat component, a positive j hat component, and a negative, fairly large, they're actually all fairly large, and a negative z component or k hat component. All right, and then I drew it. There it is. All right, we can see it's going way off in the negative direction. It goes up a little bit in y, so you can see it moves up a little bit, but mostly it's going to go back in, it's going to go backwards in z, so it's going back into the page as shown here, and it's going in the negative x direction as shown at this dotted line. Okay, all right, so there is our vector. All right, let's do it for angular momentum. So suppose you have a position vector r, given as this, and you have an angular, and then you're asked for the angular momentum vector, so we want to find L, and we're given a translational momentum vector P, and and that's actually in that one just points along the x-axis, along the negative x-axis, because it's just negative 10 I hat, okay, Newton seconds. All right, so the picture would look like this. There's our translational momentum vector, just pointing straight in the negative x direction. We've got our R, our displacement vector, which has a positive I hat and positive k hat, so it's in the xz plane, right, as you can see. And notice I pointed out that it has a component, a perpendicular component, that the perpendicular here is measured relative to P, right? And that perpendicular component also happens to be its Z component, okay? And that's just because of the way things work out, especially because the P vector is entirely in the negative X direction. All right, so then, this is, right? So between these two, it's 90 degrees. So so in other words, the actual magnitude of L, if we're just interested in its magnitude, which we're not, but it would be P times RZ. There you go. That would be the magnitude of L. Cool, right? Because the angle between RZ and P is 90 degrees, and sine of 90 degrees is 1. All right. So, but let's go ahead and actually do the cross product, because we want to find the actual vector form of L. All right. Because when you're asked for the angular momentum and you're not asked for its magnitude, you better assume it's a vector. Okay. So then L is R cross P. All right. Set up our little reminder, which is our 3x3 determinant. All right. Group everything together. Here I left everything symbolic because a lot of it's just going to become zeros, all right? And basically, most of it's going to become zeros, right? Because if you think about it, P only has, the only thing that P has that is non-zero is its x component. So anything that has any component of P that's not Px will just automatically zero out. So I look over here, well, Pz is 0, good. Py is 0, okay. Pz is 0, great. Oh, okay, this one actually has a Px, okay, so that one will potentially survive. But let's double check. We need R, and okay, well, RZ is also non-zero, so yes, this one will definitely survive, okay? Moving on, well, PY, that's 0. PX, okay, so this one should also survive, but actually, look, R doesn't even have a y component. R only has an x and a z component. So actually this one's also 0. That means there's only one single term that survives, the one attached to j hat. Okay? And so then when we work it out, we are going to have a negative, a negative, and a negative. So we'll end up with a negative. All right? And it's going to be entirely in the j hat direction. And there we have it, negative 14 joule seconds. All right? In the j hat direction. So in other words, in the negative y direction. So it should point straight down. What does it look like? There it is. Okay? I didn't really draw in perspective so much, but you have to imagine it pointing straight down, right? Continuing along the y-axis, but in the negative direction. And is this consistent with the right-hand rule? Let's see. Take your right hand, right? Bear with me here. Use your index finger for R, which point it towards you, straight towards you out of the page. Then take your middle finger and point it towards your left, okay? All right? And that forces, you can have to kind of turn your arm awkwardly, but that forces your thumb to point where? Straight down. Exactly what we found. Great. We're done, right? And we got the value. Okay. All right, so there's a couple ones of constant vectors. Let's do the same thing, but with time-dependent vectors. All right, example 3. Suppose a position vector r of a particle with mass 0.2 kilograms is the following expression, right? 5t I hat plus this parabolic expression here, negative 1.2 t squared plus 4 j hat plus 4t k hat, okay? So this is r as a function of t. So it's a vector and a function, okay? Great, all right? And then the position vector is measured relative to the origin, and begins at t equals 0, okay? And the question, is what is tau about the origin? Okay, so that's going to be the function of tau. And then what is tau after 2 seconds? Okay. Now we don't know for sure. You don't, I mean when you do this sort of thing, since you're already taking derivatives, you don't, unless you have a lot of practice with it, you don't know for sure if just because you have a time-dependent position vector means that you're going to have a time-dependent torque vector. It kind of it depends on the order of the function here. You know, maybe if it's all linear, then maybe your torque vector will be constant. Okay. But it's probably not going to be, considering I'm asking for it at a particular time. All right. But again, you don't know for sure. All right. So let's go ahead and start off with a picture. This is actually the trajectory in 3D. How would I know this? Well, think about it, right? We've got linear behavior in the x direction. We've got linear behavior in the z direction. All right. Well, that's represented by this red dotted line, right? Because it's basically growing linearly in z and x. Okay. Meanwhile, we have, and both of those would start at 0, because if you plug in t equals 0, you get x equals 0 and z equals 0, right? On the other hand, if you plug in t equals 0, you get an initial value of 4y. See? So that's why it starts right there at t equals 0. That's the kind of the initial location, the starting point. And if you look at it in the y direction, it's a downward facing parabola, right? So that's the idea. It's a parabola that's kind of coming out of the page and to your right. That's what this trajectory in 3D is supposed to represent. I think it looks like it, right? Okay, so there's our cool 3D parabola, and let's think about what that means for the actual torque that is created. Now we think about it, we have this idea of torque, right? So, and we should be able to curl our hand kind of in the direction, our thumb should stick in, perpendicular to the plane of rotation. So since this parabola is essentially a plane of rotation, that means torque should probably point off somewhere that way, right? Kind of back into the page and also to the right. Okay? Now, it's not going to be perfect because this isn't circular motion, this is parabolic motion. So it's not going to be exactly like you would expect from curling your fingers and making that assumption of circular motion. But still, we should generally expect torque to point back into the page and to the right. Okay? All right. So we'll use the cross product definition of torque. All right. Now notice what I do. I use Newton's second law. The first time we ever saw it, F equals ma. Why did I do that? Well, because I'm going to go from r to a. So notice what I do. I'm going to take the derivative of my position function to get a velocity function. Okay? So let's see what I do. I just take the derivative with respect to time of the whole vector. Okay? Because it's a vector function. 5t I hat, negative 1.2 t squared plus 4j hat, 4t k hat, right? Just as written in the problem. All right, so just go ahead and do the rules of derivatives for polynomials, and we get this, okay? So we see that our velocity vector is, well, nearly constant, but it is still time dependent in the j hat direction, okay? So essentially, what the velocity vector would look like, it would, if we were to draw it, it would just have, one value, and then it would just be growing in the y direction, right? It would be just like growing downwards, okay? It'd just be getting longer and longer, but it'd have a fixed location in x and z. Okay, well, what about acceleration? All right, well, acceleration is just going to be the first time derivative of that. All right, well, that's pretty easy because constants just go away. So we're just left with constant. Well, and just 2.4, right? Because it's just, the t is just going to become 1. So there we go. So that means our acceleration points in the negative j hat direction. In other words, the negative y direction, right? So essentially acceleration is right there, right? And it's a fixed vector. Okay, wonderful. Now we'll actually go ahead and do the cross product, okay? So then tau is going to be r cross ma. The m is going to come out. All right, so then up top, I'm going to have my tau vector, right, with all the t's and everything. But down below, representing the acceleration vector, it's pretty simple, right, because there's 0 times a constant and a 0. So that means the actual cross product should be fairly simple to calculate. So we'll go ahead and look at our terms here, right? We look, and I'm still leaving the m out in front, but a lot of things are just going to become 0. We got a 0 there. Everything attached to j just becomes 0. So there's no component of torque that's in a point in the y direction. That makes sense because having torque point in the y direction makes no sense based on the right-hand rule. There's no way any part of torque should point that way because that is the plane of rotation, right? Okay, and so then at least it is on the plane of rotation. Anyway, so then we have in the k hat direction there is one non-zero term. All right, clean things up a little bit. Right, we got our 200 grams or 0.2 kilograms in front, and then I'll distribute that in, and there is our final answer. Units of Newton meters. All right, and we see that it actually is linear. So essentially the torque vector is growing. But that makes sense because think, parabolic motion, unlike circular motion, is getting steeper and steeper, right? Because that's the nature of parabolas, which means the torque vector is always pointing. Look, it's got a positive component in I hat and a negative component in k hat. So indeed it is pointing back into the page and to the right, and it's growing. So over time, it's just going to get longer and longer and longer as the parabola gets steeper and steeper. Okay, so now let's find it at 2 seconds. All right, so there it is at least at a particular time, and at 2 seconds we'll just plug in t equals 2 for the t's that show up on both the components that survived, and we get 3.84 newton meters minus 4.8 newton meters. Well, 3.84 newton meters I hat minus 4.8 newton meters k hat. That is our torque vector at 2 seconds. All right, so it is a time-dependent torque. All right, let's do it now for angular momentum. All right, so if you look, you might be like, wait, it's the same equation. What's going on, right? Look, it's the same exact position equation, same mass, same everything. But I'm asking for a different thing. I'm asking for angular momentum about the origin instead of torque this time. So in example 4, the only thing that's different is angular momentum because I wanted to highlight that. But then if you look at part B, I actually asked for the torque. So you'd be like, wait, we know that. It's this, right? Why am I, is this a typo? Well, no, because what I want to show in part B, when we get to it in just a moment, is that we can find torque through using Newton's law in angular momentum form. Basically just taking the derivative of angular momentum to get back to torque. So in other words, you can get to torque through the cross product, or you can get to torque through the derivative of the angular momentum vector. You'll get the same answer either way, as you should, right? Okay, so let's go ahead and work this out. All right, so there's our 3D trajectory again. All right, and this time we're going to be doing the cross product, but for angular momentum, which is r cross mv or r cross p, right? Of course, p is mv. Okay, factor out the m. But before we do that, we'll just, again, do our first time derivative, but we've already done this, right? Okay, but we don't have to do a second one because we don't care about acceleration this time, right? So it saves us one derivative now, right? But we'll end up having to do a derivative later on to get torque. All right, so clean things up. I kept everything symbolic, but then I plug in the numbers. Okay, all right, and again, this is just doing the determinant, all right? And I just plugged in all the appropriate components. And there we go, all right? There is our angular momentum vector. So that's interesting because it's definitely different. It is time dependent just like torque, but it's dependent on the squared, okay? So the angular momentum vector is definitely, it basically points in the same direction. Look, it's got its component in the I hat direction is always going to be positive, so it always points to the right, and its component in the k hat direction is always going to be negative, and so it's always going to point back into the page. It doesn't have a j hat component, right? The units are joule seconds. Important to mention that, right? But it's going to be growing faster. It's going to be growing with the square of time, okay? And it's also not 0 at t equals 0, okay? Unlike torque, which was 0 at t equals 0. Okay, that's interesting. All right, so there it is, right? I drew it a little bit longer, maybe to compare. All right, and then let's go ahead and show that we can get the same torque vector by taking the first time derivative of angular momentum. So for part B, to find torque, I'm going to take this angular momentum vector and just take its derivative with respect to time. All right, so literally I just take the derivative, essentially distributed in this operator, right, into both the I hat and k hat component, right, 0.2 out in front. Okay, work everything out, and there we go. There is our torque vector. Is it the same answer? Sure is, right? The exact same answer, right? Because I'm not asking for a particular time, so it'd be it's the function form, not the form at t equals 2 seconds. See, same vector, okay? And there it is. So here's an interesting thing, okay? So because torque it equals dl dt, that means that torque and dl are parallel. They're always parallel to each other. So whatever direction torque points, the torque vector, the instantaneous change in angular momentum vector also points in that same direction. Okay, that's great. But notice what that isn't saying. That's not saying that torque and L are parallel, because they're not. Torque and angular momentum are not necessarily parallel. In fact, here we can see an example where they're definitely not. But let's think about this. So if we think about torque, right, torque points in the direction of dl. So I can imagine taking this torque vector and kind of attacking it on tip-to-tail vector addition in a tip-to-tail vector addition manner. So I put it over here. Here's my torque vector. So that would mean that some moment later, maybe some infinitesimal time step later, I would have a new angular momentum vector, which would be the sum of those two vectors, right? So this would be like my L final as t grows. So we can see that what's happening is, both tau and L are growing, but we can always find that the reason L is growing faster is every time we find a new angular momentum vector, we tack on the existing torque vector and then do tip-to-tail addition to find the new angular momentum vector. So if we add a bigger torque vector, then our new angular momentum vector is even longer. Okay? Then that's literally what's happening. The angular momentum vector is chasing the torque vector because the torque vector points parallel to dl. All right? I bring that up because that's actually the best way to understand gyroscopic motion, which we'll talk about as our third and final lecture for this chapter. Okay? But it's good to already kind of think about the idea now. All right. So one final example, one that's not going to involve any cross products. All right? An actual object, not just a coordinate axis. Okay? All right. So example 5. A radio transmitter tower has a mass of 80 kilograms and is 12 meters high. The tower is anchored to the ground by a flexible joint, so somewhere down there, at its base, but is secured by 3 cables at 120 degrees apart as shown. If one of the cables broke, the tower would fall away from the broken cable, rotating about its base. What would be the speed at the top of the tower as a function of the rotation angle theta? All right? And note that start the analysis with Newton's second law in angular momentum form and approximate the tall tower as a rod of uniform density. All right? Okay. And then finally in part B, we're going to show these results agree with those obtained through conservation of energy. And you'll see what I mean by that in a minute. Okay. And by the way, this 120 degrees business doesn't show up at all. It actually is completely irrelevant. We do care about the starting angle, but we're going to keep it symbolic because we want a function of that angle. All right. But we're all going to have other actual values in terms of the 80 kilograms and 12 meters. All right. Okay. Notice up here that we point out that velocity is equal to length times omega. All right. That's just the relationship between translational velocity and omega. Often though, I always write as v equals r omega if the L is confusing you, okay? And this is not L for angular momentum, this is L for length, right? This is the length of the rod, okay? And again, this is the translational velocity of the tip of the rod, okay? All right, so how do we go about doing this? Well, we're going to consider a displacement vector to the actual point of application of force, because the force, as we know, is only applied at the center of mass, okay? So the center of mass is right here, so the displacement vector from the pivot point to the center of mass is r. There's also a component of r, which is perpendicular to the force, which we call r perpendicular. No surprise there, okay? All right, so then we're going to set up torque. All right, so torque then, by definition, is dl dt. Probably should be a vector there. All right, and we're going to also acknowledge that torque is then just equal to in magnitude, is going to be equal to the force, the entire gravitational force, so Fg, times the perpendicular component of the displacement vector, the moment arm, r perpendicular. Okay, all right. And dl dt can be rewritten, because this is a solid object after all, as d of I omega over dt. In other words, taking the first time derivative of I omega. Okay? Okay, and this is for solid objects, which the tower definitely is, I omega. Okay? And for a rod rotating about at one end, we can actually put in our well-known published Moment of inertia for a rod, uniform rod, rotating about 1 n, 1/3 ml squared. Okay, all right. Okay, so that means that Newton's second law now has changed a bit. Okay, well, we'll bring it all together. But first of all, we'll only look at the left-hand side of, or right-hand side of Newton's second law. So this side has changed. dl over dt now becomes d over dt of 1/3 ml squared omega. Okay, looks good. All right, what comes out? Well, these are all constants. They're not time dependent, so they come out of the derivative. But the omega doesn't, because the omega is definitely not constant. It depends on time, right? Because the rod is obviously going to be speeding up as it falls. That's common sense. Okay? All right, and then we'll go back to Newton's second law, bring everything together. Okay, so notice what I do here. I'm expressing torque as its magnitude, which is Fg times r perpendicular, which is just mg times r sine theta. Why r sine theta? Well, because r perpendicular is r sine theta, right? Okay, great. So that's our left-hand side of the equation. That's the torque side. Meanwhile, we already know what the right-hand side looks like. It just looks like 1/3 ml squared times the first-time derivative of angular velocity, d omega over dt. Okay, so where are we going with this? Well, we want to find an expression of the translational velocity at the top of the tower as a function of theta. Okay, we're not quite there yet, right? Because so far I just have some derivative. How am I going to get a function? Well, first of all, we're going to maybe, multiply by our differentials, right? We're going to get everything that's a function of omega on one side, get everything that's a function of time on the other side, and then, just go from there. Just take it, basically end up integrating. But before we do that, we need to do a differential substitution. We need to rewrite this d omega over dt as something that's going to work better for us. What do I mean by that? Well, I want to write it as something that has theta in it. Because that's the thing, right? If you think about it, angle and omega, they're related to each other. Because, it's speeding up as it falls. And it speeds up as it falls because the angle gets bigger. Because then there's more force, So there's, so there definitely should be a relationship between these two. But how do we show it? Well, like this. We take our d omega over dt and we just put in a d theta, all right? Because d theta over d theta is just 1. So multiplying each side of the equation by 1 is totally allowed, all right? So we can imagine that I multiplied the left-hand side of the equation by 1, and that just left it there. But I multiplied the right-hand side of the equation by 1 as well, but by 1 in the form of d theta over d theta. And then I distribute it, so then I got a d omega over d theta and a d theta over dt. Okay, well that means that my d omega over d theta is just kind of sticking with us for now. It's just going to stay. But look what d theta over dt becomes. By definition, it's omega, angular velocity. Interesting. Okay, so that's all we've done here. We've done a differential substitution to change the right-hand side of the equation from this to this. Okay, so why would we do that? Because we want to integrate. Because what I'm going to do now is I'm going to multiply both sides by d theta, right? Because before it's like I had a dt. What was dt? I didn't know. I don't know what theta's dependence is on time, right? Now we can get there. It turns out that we can come up with some expression for that, but we're not there yet. We don't actually have the tools. We have to really actually solve a differential equation. But instead, now that I have a d theta, I can clearly see that this is a function of theta, and that's a differential of theta, which means I should put them together. In other words, I'm just going to multiply both sides of the equation by d theta, which will then cancel them out on the right-hand side and leave me with 1 on the left-hand side where I want it. Okay? And then also note that r is just L over 2, which is nice because then we're not going to have unnecessary variables because we know what r is in terms of L. Okay? All right. So what I do here, I multiply both sides by d theta. Okay, so we got that. I still actually left that as r. Probably should have already replaced it with L over 2, but we'll do it later. All right, and then over on the right-hand side, I've got n omega d omega. Now we're ready to integrate. Okay? Check it out. And it's going to be a definite integral. We're going to integrate from 0 to theta because we're trying to find a function on the left-hand side, and we're going to integrate from 0 to omega, again, because we're trying to find a function. Okay? Both of these have some variable and some differentials that match up. Okay? That's the key here. Okay? And so when we actually solve the integrals, on the left-hand side, the sine theta, the antiderivative is going to give us, let's see, so if we have, let's make sure, I'm just going to reason this out. So if I have sine, right, so sine is moving up and positive, which means so that the derivative of sine is going to be positive cosine. And so then if I'm taking the antiderivative of sine, then I should get negative cosine, okay? and then I evaluate the two limits, and when I evaluate the upper limit minus the lower limit, and then basically reorient them so that I don't have the leading negative, this is what I get from doing the limits. Notice also that I factored out the constant 1/2 over g, just brought it out of the integral. All right. And then on the right-hand side, we don't have to worry about any antiderivatives of trig functions because it's just simply a polynomial, right? The omega just becomes omega squared over 2. The 2 times 3 becomes a 6. Okay? All right. And then we're just going to go ahead and actually solve for omega. All right. So now we have omega as a function of theta. This is how fast the rod is falling, the radio tower, as the angle grows. Because the bigger the angle, the bigger the torque, which means the faster it falls, the faster the rate at which it falls. All right. So here we have this growing function of its angular velocity. And we were asked for its translational velocity at the tip. So all we want to do is just remember that the velocity at the top is just omega times L. So we'll just multiply by L. All right. And I just distribute the L into the integral, or not, it's not an integral, excuse me, into the square root. And when I distribute the L into the square root, basically an L outside of the square root becomes an L squared inside of the square root, which means it cancels with the one in the denominator and leaves one up top in the numerator. So there's our final expression for the translational velocity of the tip of the radio tower as it falls as a function of the angle theta, which is the angle measured with the vertical direction. Okay, great. That took a lot of work to get, right? But still, it's nice to see that these ideas unite, that they come together, that there is a common thread. Because, check it out, we can get the same exact result, much easier, mind you, with conservation of energy. Okay, so let's quickly do that, because that's what we're asked for in part B, by the way, is show that these results agree with those obtainable through conservation of energy. All right, so from energy conservation, we'd simply use mgh equals 1/2 I omega squared in order to find omega, right? Because the idea is that when the system starts from rest, it has entirely gravitational potential energy, which is the gravitational potential energy of its center of mass. That's the way these things work, okay? Because that's the only place where the gravitational force acts. Its kinetic energy is entirely rotational kinetic energy because it is not translating, right? The object is not translating, it's rotating. It's not rolling, it's just rotating without translation, okay? So then we'd acknowledge that for theta equals 90 degrees, then that's going to be the final state, okay? Then I'm simply going to solve for v, all right? And then I get a final velocity of the square root of 3lg, okay? And that's totally consistent with what I would have got if I plug in theta equals 90 degrees into that function, okay? So again, I just did it for simplicity, just to show that it worked for one version of theta. And that's the thing here, is that this isn't going to have theta show up in it. We'd have to plug them in one at a time and show that they match up. But arguably, if it works for this angle, then it should work for any other angle. You could try 45 degrees and you'll see that they work as well. But the nice thing about 90 degrees is it shows it really clearly, because cosine of theta right here is just going to be, cosine of 90 is going to be 0, which means then that this expression just becomes the square root of 3gl, which is exactly what we get from conservation of energy. Okay? All right. So there you have it, using Newton's second law in rotational form and the relationships between angular momentum, angular velocity, and torque. Okay? All right. Well, I hope this lecture has been interesting and informative. Please message me if you have any questions about the content. All right. Bye for now.